but to be able to give you an idea how to appreciate such a laser infrastructure, I'll give an introductory talk about high energy short pulses. So welcome to Szeged, which is not just the city of sunshine, but also the city of a very intense laser light source. The outline of my talk, let me use the logo to explain what I'm going to talk about. So first I'm going to give you a brief introduction to the ELI project that is hidden in the name of the summer school. Then I'm going to tell you about lasers, and especially short pulse lasers. And then I'm going to tell you what is the connection between lasers and medicine and life sciences, so the application of lasers in medicine. And for the S, it's summer. So basically ELI is an acronym. It stands for Extreme Light Infrastructure. This is a European research institute which is on the S3 roadmap. So this is some strategical collection of large-scale research infrastructures, and it is going to be implemented in 3 sites. The middle one is denoting Szeged, and there is one site close to Bucharest, in Magyarul, and there is one research infrastructure close to Prague. The 3 research infrastructures are complementary. They are all based on laser, high-power laser systems, but the specifications and the type of research that you can do with them is complementary. The missions of ELI infrastructure is to contribute to technological development of laser science, because we are now trying to push the limits of laser science. And also each of the research infrastructures has a specific goal to fulfill. For the Hungarian sites that we also call ELI-ALPS, which is a bit funny because we are on a great plane, but we try to bring this infrastructure to the peak, to a height, is to generate attosecond pulses. So this is what the name comes from, attosecond light pulse source. So just to give you a hint about the length of an attosecond, so attosecond is 10 to the minus 18 seconds. Light travels 300,000 kilometers in each second, so in each second light can travel around the equator of Earth 7.5 times. And in shorter times, of course, light can travel shorter distances in 1 attosecond, which is 0.1707 then a 1. The light can travel the width of a water molecule. So this is the time scale or the length scale of attosecond pulses. This is what our research institute looks like, and actually it looks like this. You're going on a site visit next Thursday, if I'm not mistaken. Wednesday, sorry. So next Wednesday, and this is what you're going to see. This is the building, the technological building where the lasers will be positioned, and the other buildings are supplementary, they possess supplementary roles. This is how it all started. Well, I should say the whole research project started a bit earlier. In 2005, a French scientist, Gérard Bourou, thought about a European laser infrastructure, and then it took some while to get financing, because that's always the crucial point about research and everything else in life. And in 2012, when there were just green fields in the area that used to be a Soviet military base, construction started, first by removing vegetation and removing bombs that were hidden under the surface. And then after a few years of construction, and the landscape looked like this, and at a later point architecture aspect, this was a really big challenge to be built. And this photo I took in January, but it looks very similar to now because the exterior of the building has been ready by last December. Now some greenery is added, but other than that, it's the inside of the building which is now being developed. So as I said, this is the technological building, the darkest grey one, and this is where the laser technology will be positioned and experiments as well. And then we have additionally 3 more buildings. This is what we call the Science Center. This will house some offices and a big lecture hall. So I hope that in a later year, this summer school we can also host at ELI. In this building B, we have offices and supplementary scientific and technical laboratories. This will host the laboratories that don't require the precision of the high-intensity laser lab. And then we have an additional service building to support working at the ELI infrastructure. Just a few interesting facts about the construction. A huge amount of ground had to be removed, most of it from underneath the technological building, because the foundations need to be very, very stable. Vibration isolation need to be achieved, and really the stability was a crucial point. So this building is standing on piles, 819 piles altogether, and if you sum up the length of the piles, it sums up to more than 14 kilometers. This is what the inside of the building look like, and you might be able to see it with your own eyes. We have a crane system inside the buildings to allow us to position our big chambers, which will hold experiments, and that will also hold the lasers and optical tables, of course. This is the preparation labs. We already started moving in furniture to these parts of the building. This is the lecture hall that I have mentioned before. According to the architect's notion, this orange thing resembles the brain, to emphasize that this is really some scientific institute. And inside this brain, the ground floor of it is a lecture theater that can house 200 or 250 seats, and the top floor will be a library. So the main purpose of this whole research institute to have cutting-edge laser systems. This is the different laser systems that we are procuring, and here I list 4 different lasers, and I'm saying that they are all cutting edge. They are all whatever can be achieved today in laser technology. And I indicate here with some numbers or the specifications that these lasers will be able to provide. And I'll come back to it later after I've told you what are the main characteristics of lasers, so that we can appreciate it a bit more. But just to give you a hint about what these lasers, what it means that we are pushing the limits of laser technology, in this plot, in this graph, I have some very well-known famous research institutes lasers parameters plotted, and this is what we are aiming for at ELI. And here, the higher and the leftward, the better the laser. There is actually a proposal to build a laser in Garching in Germany that is even exceeding our laser source. but we are closer to the implementation. And I think all these laser systems, we will be able to improve the characteristics by an order of magnitude in pulse energy and also shortening the pulse duration. So I'm now going to talk about lasers, the basic principles of lasers. What is a laser? Laser is an acronym. If you just look at the word, it stands for light amplification by stimulated emission of radiation. So first I'm going to tell you what this stimulated emission of radiation means. But in principle, what you need to know about lasers is that laser is a light source, and this light has very special properties. And these very special properties are actually derived from the method of generating this light. From the simulated emission of radiation, the architecture of the laser. The idea of building lasers originates from Einstein from 1916, when he described the physics of this stimulated emission. The first laser was built by Maiman in 1960, so you can see that it took a long way from idea to realization, because it was a non-trivial exercise. And in 1960, the first scientific laboratory laser was shooting, but very soon after that, it became part of the knowledge of people through films. So you might remember in the James Bond film, the laser was used to cut, not Bond, but the table underneath him, and in Star Wars, lasers were used as weapons. And at that time, we thought, oh, this is just fiction. But now, we actually do use lasers to cut metal. In most car-producing companies, they use lasers. And also in the military, they use lasers because they can now be made so intense. This is what a laser laboratory looks like. It's kind of disappointing. What you see is just boxes, but we know that in the boxes there are some shiny pieces, and if you know well how to position these shiny pieces, then you can make a laser. Lasers nowadays are all around us. It's very difficult to imagine what we could do without lasers. So the CD player, DVD players, barcode scanners. Lasers are very widely used in medicine, and this is why this summer school is actually being organized. And during this week, you're going to learn a lot about applications of lasers in different fields of medicine. But holography, as I said, in industry, cutting with lasers, and in research we also use lasers. So the basic questions that I'm going to touch today, and I hope by the end of the lecture you will be able to answer to all of these. So what is a laser? What is its specialty? How the special properties come about? The main components of a laser that actually lead to these special properties, and finally, what properties of these lasers qualify them an ideal tool for medical applications. Building a laser from the physicist's point of view is like Lego. You have these pieces and you have to position them in the right way, and then you get a laser. And laser, as I said, is a light source. It gives you some very special property lights, but basically whatever you produce with the laser follows the rules of ordinary optics. So you can use lenses and mirrors to focus them. If they reach a boundary and interface between two media, they refract. And also, as we know about light, light can have different frequencies, different wavelengths. These two parameters that we describe the laser with are defined by the speed of the light in the given medium. So what are the special properties? The special properties of laser light are monochromaticity. This word means that it's monochrome, single color, so the light that the lasers produce has a very well-defined color. The color corresponds to very well-defined wavelength or very well-defined frequency. Let me remind you of the previous figure. So depending on the color of visible light, it corresponds to different wavelengths, but we can extend this notion of color to the non-visible ranges of electromagnetic radiation. So monochromaticity means that laser light has a very well-defined color. It has a narrow bandwidth. So here on this figure I can show you that visible light ranges from 400 to approximately 700 nanometers or 4,000 to 6,000 angstroms. A spectral lamp which already has defined wavelength ranges, so defined spectra, would correspond to something like this with respect to the visible range, and the laser line width is so narrow that we just indicate it with a single line. This property of monochromaticity also somehow leads to a property that we call temporal coherence. Coherence means that it's a very well-behaved wave. So this is a very well-behaving wave. This wave has a bit of non-well-behaving, so it has some breakage between time intervals, and this is an even messier version of a light wave. But lasers produce something that behaves well for a long time. This means temporal coherence. The light that we produce in light bulbs or these things on the ceiling, in time it's not an ordered, not a well-ordered sinusoidal wave, so it's difficult to describe with a sinusoidal wave. A different class of these special properties is the spatial properties of the light that the lasers produce. Laser light is very well collimated. Collimated means that it's very parallel. So if you would take a big laser and you would shoot to the moon, it would still be in a well-defined cylinder, or a well-defined cone. So this is why they can make this light traveling around the globe, that with the laser they shine to the next city and then it bounces from a mirror, because it keeps its collimated ray. It also leads to the property that this light can be focused into a very small spot. Opposite to the light of the sun, the light of a light bulb, there is a limit to which you can focus it down to. Laser lights can be focused to a very tiny spot, which means that we can concentrate in space the energy that we have in the laser light. And very similarly to the temporal coherence, laser light can be said to have a very good spatial coherence as well. So not just temporally, but also spatially, the wavefront or the phase front behaves very nicely, so different parts of the light can be used to produce interference. Additionally to these, the other properties of laser lights are tunability, so you can actually change this very well-defined color of your laser in a given range of course, but you can build lasers that have a variable wavelength. From lasers we can create really short bursts of light, really short pulse durations are available. The first lasers that I mentioned, the 1961, produced a pulse of 10 to the minus 9, a nanosecond range. But since then, there was a lot of progress in laser technology, and now we can routinely make femtosecond pulses, so this is 10 to the minus 15th of a second. An attosecond is still 1,000 times shorter than the femtosecond. but we can, as I said, routinely make with lasers these femtosecond pulses. And the good focusability means that we can concentrate the laser light energy to a small spot, a small spatial dimension. The short pulse duration means that we can concentrate the energy to a very short time interval, so we can actually reach very high intensity, very intense fields, very intense electric fields by using lasers. So I promise you that I'll tell you something about this stimulated emission of radiation so that we can appreciate how laser light is being produced. In quantum physics, we describe light in bunches of energy. This is what we call the photon. And in quantum mechanics, quantum physics, it is one of the postulates that matter and light can only exchange energy in forms of these energy packets in these photons. So a matter, an atom for simplicity, can be in different energy states, and it can either be in a ground state or in an excited state. That's the two options. And we can illuminate it with light that could bring additional energy to the system. And let's assume that the ground state and the excited state has an energy difference which is equivalent to the energy of the photon, so it's easy to communicate between light and matter. If we have our atom in a ground state and an incoming photon, what can happen? Either the photon just passes by or the photon is being absorbed. If the photon is being absorbed, then we have no photon going out because it's lost, but the atom goes to the excited state. So this is one fundamental process. The inverse of it is if we have the initial state of the atom in the excited state, but there is no photon, then since everything wants to go to the lowest possible energy level, this atom can emit the energy in form of a photon and then decay to the ground states. This is the second fundamental process. And this has been known before Einstein, but he thought that there could be a third process, which is also allowed, that we have the excited state, like for this case, and we have the photon coming in. And if this photon initiates the transition of the atom from the excited state to the ground state, it means we are going to get two photons out. The main difference between these two is that these two photons are locked somehow, because one photon took part in generating the second photon. So they are in the same phase. This is why laser light is actually going to be coherent, because they are locked together. So this is the main principle behind lasers, that we have the photons locked somehow. They are joined by the stimulated emission process. And this Einstein described in 1916 that it would be a very useful, very nice light source if we could exploit somehow this process. The main problem, the technological problem is if you consider absorption and stimulated emission, so the first and the last process of my previous slide, they both contain the photon coming in and the matter. In one case, the atom is in the ground state, in the other one, the atom is in the excited state. And in one case, we have a less number, we reduce the number of photons, and the other one, we increase the number of photons. And these two processes, they compete with each other. Because incoming photon, there are two things can happen, either minus one photon or plus one photon. They compete with each other, as I said, and this process, the probability of this process is proportional to the number of atoms in the ground state, and this one is proportional to the number of excited state atoms. Which means that to be able to win, to be able to increase the number of photons, we need to have a higher probability of this process, which means we need to have a higher number of excited state atoms than ground state atoms. I keep saying atoms because it's easier to say, but it can be molecules, of course, as well. And the main problem is that in thermal equilibrium, the levels of an atom is populated that the ground state has more, it's more probable to be filled than the excited state, because, as I said, all materials of all systems tend to go to the lowest possible energy level. So what we need to reach is an inverse population state. So this is why producing laser light is a non-trivial business, because we have to reach this stage when we have more atoms in the excited state than in the ground state. We call it population inversion, and we do this by pumping the system. So, as I said, in thermal equilibrium, the lower the energy state, the higher the population, and we would like to have an inverse of it. To reach this, we need to pump the system, we need to supply energy to the system. So this invested energy is that will lead to the laser behavior. To be able to use the active medium, this medium that can provide us the stimulated emission, we put usually this active medium into a resonator, and one of the properties, one of the reason why we have this resonator is that it keeps the light bouncing back and forth, and in each round we increase the amount of light through this stimulated emission. Of course, there are always some spontaneous emission, but because of this multiple bouncing back and forth, stimulated emission will take charge. So in this cartoon, I'm trying to illustrate how the laser is operating. So basically, we have an active medium that's sometimes called lasing medium, sometimes active medium, and it's built up of atoms or molecules with a certain energy structure. Originally, before we start using the laser, all these atoms are in the ground state. The lasing medium is at the ground state, but we prepared our laser by putting this active medium between two mirrors that provide us with the oscillator resonator. Then we start pumping our laser material, so we invest some energy into exciting some of the atoms of the medium, and the ground state atoms are denoted by this greenish dot, and the excited atoms in purple. So we start increasing the number of excited state atoms, and then just spontaneously, because some of these atoms are in an excited state, spontaneous emission can occur, which means we will have a photon that will start propagating in this medium. And if this photon hits another excited state atom, it can induce stimulated emission, and then we will have two photons in phase now propagating. Then this light reaches the mirror. During the path, it might hit additional excited state atoms, and when it bounces back to the mirror, it travels really long path in this active medium. And the stimulated emission is building up. We are getting higher and higher intensity of light, higher and higher energy of light being built inside this laser cavity. One of the end mirrors of this cavity is partially reflecting. It means that a little bit of light can be leaking through. This light which is leaking through is lost for the lasing process. It's not being amplified further. But this loss, this leakage is actually the laser light that we can use. So this is the laser light that we use. There is always a much higher intensity of light inside the cavity than what is coming out. But this is what we can use for application. But we need a feedback to keep amplifying the light. So these are the main parts of the lasers, and I told you building laser is like Lego. You have to have the different parts and you build them together. So basically the number one is the laser material, and it can be of different types. I'm going to show you some examples of gas lasers, liquid state lasers, solid state lasers, and this is used to generate and amplify light. Very important, we need an additional pumping, a source of energy to create and maintain population inversion. This again can be very different types. We can use an electric current. In some lasers it's chemical reaction that is being used. Or it can be some very intense form of light. Sometimes we use one laser to pump another laser. Sometimes it's just a flashlight which is pumping the active medium. Number 3 and 4 are the mirrors of the optical cavity, and they are used to feed light back to the active medium. One is a perfect mirror, as high reflectivity as we can make. Almost 100%. Very little is being lost on this mirror. The other one is a partial reflector. So sometimes there is a loss of 1%, sometimes even less than 1%, sometimes a bit more, a few percent. And this is to couple out the light from the cavity, and this is the light that we are going to use in our laser applications. And of course, additionally to this, which is not on this schematic drawing, we need voltage supplies, we need control system, we need cooling of certain parts of the laser. So if you look at a laser or look inside what's in the box, there are many more things to take care of. But these are the principal components that makes laser operation possible. This is what the first laser looked like, 1916. This was a ruby laser. So there was a rod, a glass rod, which was doped with the atoms that could produce stimulated emission. It was brought into population inversion. It was pumped by a flash tube. Actually, the flash tube is this glass thing which is wound around for better illuminating the active material from all sides. And the end mirrors were actually the ends of this ruby rod. Some reflecting material evaporated on them. So it's a very compact system. Depending on what's the active medium, each active medium has a very well-defined wavelength range that it can be used to amplify light. So on this figure, I'm showing you a few types of laser materials, and it defines very definitely what is the wavelength of the laser light that you can produce. And it's important to know what laser wavelength you can use for a certain application, because everything has a well-defined absorption curve. This is the absorption curve of some biologically interesting materials. Between 300 nanometer and 2000 nanometer, you can see that the absorption varies many orders of magnitude. It's in logarithmic scale. So you have to choose the laser to your application, and you use it by selecting what wavelength I want to address my sample with, and then you have to choose what laser material can be used to amplify that wavelength. I'm going to describe now each part of the laser in a bit more detail than what I've said before. First, I'm going to talk about the active medium. I said that the active medium can come in different forms. It can be different type of material. The simplest one is if we take some gas or gas mixture to be our active medium. Gas discharges, so you have to excite the gas through a discharge, and it has been found to amplify light coherently, so it is able to work as an active medium in a laser. Sometimes the most well-known laser is probably the helium neon laser that is being used as a targeting laser for many applications. It's a mixture of helium and neon, and you excite by electron collision the helium, and then it transfers some energy to the neon atoms, and this is how you actually reach the population inversion in neon. So this is the direction of the process it goes, and then this is how you populate the higher state of neon, and then you reach a state where the higher energy level is populated more than the ground state. Different gases can be used, or gas mixtures. Some lasers use noble gases, some uses ions or molecules, metal vapors, neutral atoms. A special type of gas laser is the excimer laser. The excimer is a very special molecule that only exists in its excited state. So it's built up of two parts, and it can only exist in the excited state. When it would fall down to the ground state, it dissociates. So it's a very intuitive way how we can claim that we have population inversion, because it only the ground state is empty because it doesn't exist. So we have this molecule in an excited state, and of course it has a higher population in the excited state than the empty ground state. Second type, coming from gas, the next phase of material is liquid. We can use liquids as well for active materials in lasers. The great advantage of using a liquid is that there is a much higher density of particles that can take place in the lasing process. Usually these are large organic molecules that we dissolve in a suitable liquid, ethanol, methanol, even sometimes in water. And depending on the type of the molecule, different wavelength ranges can be addressed. And what you see on this figure is the spectral range that each of these dyes, laser dyes that I list here, can amplify light. And these bandwidths, it can span more than 50 nanometers, which means you build a laser from this laser dye as its active medium, and within that range you can actually tune your laser. So it's not like I have an experiment in mind where I want to use 620 nanometer laser light, then I choose a certain gas that has a transition at 620 nanometer, and then I use that laser, and during my experiment I figure out, wow, 630 would be even more beneficial, and then I have to choose a different type of laser material. For dyes there is a limit, of course, but they are tunable. So this is one of the reasons why dye lasers were used. This would be the basic principle. dye laser, we have a cuvette containing the dye solution. We have to bring it again up to population inversion. We have to excite the material, and this is done usually in form of a pump beam, in form of light. And if we focus this light with a cylindrical lens, it means that the focal volume will be aligned, and along this line we will have the excited molecules for our liquid laser. And then we have the two mirrors in the end that makes this green beam bouncing back and forth and being amplified. I have here two photographs of a dye laser. Here the active medium is rhodanine-6G, and here it's coumarin. You can see from the color that it glows at that really different colors can be produced. And if you tune this cavity with some optical components, you can change what wavelengths your laser will be operating at. It's very easy to tune, as I said, the dye lasers.
So in this case, we can pump it only with lasers.
Yes. And I'll come back to it later, but yeah, I can also mention it to you now, that sometimes we use a laser to pump another laser, because this other laser has some property which is different from our pumping laser. So for example, we can use a fixed wavelength laser to pump our dye laser. That will be tunable. So in this way, once you have a laser light, you don't just stop with it, but you pump your laser with this laser and another laser that has a property that your original didn't have. And then you sometimes have a chain of lasers with one laser. And also at ELI, I'll comment on this with respect to ELI as well. We buy pump lasers to pump our short pulses.